I got the opportunity to still do this in person. Now, this is work with a number of my colleagues at Amazon, where I've been doing some work for the last 8 years or so. So in particular with Pat Byrie, Brian Burdick, James McQueen, Lorenzo Macerero, Thomas Richardson, and Ido Rosen. And so the work in general is sort of part of a project on experimental designs, as well as the analysis of those experiments. But it's primarily about experimental designs in settings that are more complicated, more complex than the standard experimental designs kind of that go back to the work by Fisher and Neyman, and that are widely used in drug trials, as well as also nowadays in the tech companies. In fact, there was a conference a couple of years ago where people argued that nowadays in the tech companies, many more experiments are being done than in say by the drug companies. Lots of these companies, Google, Facebook, Amazon, Uber, Lyft, are doing thousands of experiments all the time nowadays. But in many cases, the setting is much more complex than the standard one in drug trials. So in the standard case in drug trials, we have a population, we divide it in 2 or more groups. We divide it randomly in 2 or more groups. We assign units from each of these groups to a different treatment. And then we compare average outcomes in these groups. And we get simple and very clear and easily interpretable estimates of what the effect of the treatment is. So what's more complicated in these experimental settings we're considering here, and that are being considered by a number of these tech companies. The complication is that the units in these experimental settings interact with each other, and kind of not sort of in limited ways, but they interact in very general ways. Interactions kind of are intrinsic to these experimental settings, because often these settings are marketplaces, are social settings, where the fact that different units interact with each other are intrinsic to the setting. Marketplaces, by definition, about people trading objects, and often with prices in a way that the prices are affected by what other participants do. And that creates particularly challenging, that has particularly challenging implications for experimental design. And that's what we are trying to address here. So first give a little bit of an introduction, then I'll talk kind of in general about these designs that we call multiple randomization designs. And then I'll look at a simple case of that that we call the simple class of these designs called simple multiple randomization designs. And for that, we actually look at some of the designs, look at how we do estimation, and how we adjust for inference and what kind of estimates we're looking at. And then later I'll look at 2 additional designs that are more complex, but I give you some idea of the richness of these methods. And so let's kind of make this specific. Suppose we're thinking about offering customers more information about a particular product. And so to kind of make it, you can think of, say, Airbnb or VRBO, one of these rental company websites, tech companies that offer multiple properties for rent. And they have many customers as well as many properties. And we could think about offering customers, when they search for rental units, we could offer them more information about the particular rental. That information could be in the form of more pictures, or sort of pictures instead of just text information about the property, or it could be reviews from other customers about their property. And so what we're interested in is what would the outcomes be in that marketplace if we did that for all the properties and all customers. Suppose that universally we're going to present customers when they search for these rental properties, we're going to present them with more information, with more reviews, or with more pictures. And to inform, that may be costly. It may be costly to kind of set up the review process, or to take these pictures. And so before implementing that change, we want to see what the causal effect is, what the causal effect would be of doing that for everybody versus not doing that for anybody. And kind of from a conventional experimentation perspective, there would be two ways of doing such an experiment. We could randomize the rental units, randomize the products, randomize the properties to the treatment. And so say we have 8 rental properties. We could randomize 4 to the treatment group, 4 to the control group, and then look at look at the average outcome, say how often these properties got rented in a particular period or not. Alternatively, and that would be a very different experiment, but alternatively, we could randomize the customers to the treatment group or the control group. So here we have 5 customers, 3 are assigned to the treatment group, 2 are assigned to the control group, and these customers would always get the additional information, either the reviews or the pictures from those properties, and the control customers would not see those pictures or see those reviews. And so those would be 2 ways of doing the experiment. And kind of thinking about how we would analyze that, that's something we're all very familiar with. Going back to Fisher and Neyman, we would say, well, we have a population kind of with n units, a binary treatment, kind of using the Neyman-Rubin style potential outcome framework. We could think about the causal effect for each unit being the difference in the outcome. We would see if that unit was in the treatment group relative to the difference we would see for that unit if that unit was in the control group. We only see one of those, the realized outcome. But if we have a reasonably large number of units, we would then just try to estimate the average effect. We would estimate that using the difference in average outcomes for the units assigned to the treatment group minus the average outcome for the units assigned to the control group. And we would get a conservative estimator for the variance based on the work by Neyman, and we would be done. So we would get an estimate of the average effect. We would know how to do inference for that, and all would be very well. So what is the problem with doing that in the settings I just described? And so I gave one specific setting where we look at the effect of more information about properties in the rental market, but it could also be changing some of the the way customers, riders, and drivers interact in a rideshare company such as Uber or Lyft, or changing the information about products or shipping at a place like Amazon, or many of these marketplaces. And the fundamental problem is that the units interact in these marketplaces in complex but intentional ways, and that leads to spillovers between customers, that may lead to spillovers between products. So, for example, treating one customer may have an effect on the outcome for another customer. And in a rideshare company, that's very clear. If there's a treatment that makes it more attractive for me to get a ride with Uber, then that has an immediate, maybe very small, but it has an immediate effect on other customers. Because as soon as I actually get a ride, then that particular driver is not available for other riders. And so it makes the number of riders at that particular moment smaller, by only one driver, but it makes it smaller. And so it increases the competition, and it makes in principle the experience for other riders slightly less favorable. In particular, if a large number of customers are induced to get rides, that may substantially delay the time it takes to get a ride for another customer. Similar on the other side of the market, treating one product may directly affect the outcomes for other products. In rental markets, customers may decide they're looking for a place to rent in a particular period, in a particular day or particular week. And so making the rental of one property more favorable for customers means that relatively speaking, the control products become less interesting for these customers, and demand for those may go down, even though they were not directly treated. And of course, the standard A/B experiments ignore this. They don't pay attention to that. And in fact, they don't even allow us to detect the presence of this problem, or they don't allow us, and kind of directly by implication, they don't allow us to address the bias resulting from the interference. And in the type of settings we're looking at here, these spillovers, these interactions are intrinsic. They're always going to be there, because what marketplaces do is bring together different parties, different sides of a market, and facilitate trades. And if you make some trades more attractive, that often means that other trades by necessity become less attractive. And so what we're trying to do here is come up with experimental designs for this particular type of interference, where we have a marketplace, where we have two sides to a market, and we're trying to improve experimental designs over the ones that just randomize one side of the market. And so there's a sense in which it fits in kind of with a very small but kind of very recent literature, where people are also doing more complex experimentation to take account of the type of interference that comes up in tech companies and in marketplaces. And so I want to particularly mention the work by Evan Monroe, a student here at Stanford, Stefan Waage and Xiang Xu. We're looking at experimentation in markets where they allow prices to change. The work by Papadogeorgiou, Mayali and Ziegler, another paper by Ziegler and Papadogeorgiou, where they look at bipartite representations of experiments to take account of very general settings of interference, where in particular they separate the population of units that are assigned to the treatment from the population of units that outcomes are measured on. And also the work by Ramesh Johari, Hannah Lee, Inessa Liskovic, and Gabriel Weintraub, also here at Stanford, where they also look at experimental designs in two-sided platforms, and they show that standard experiments that generate bias, and they kind of show how to quantify that bias. And so the key idea of the paper here, at some level, it's a very simple one. I'm going to look at a setting where we have two populations, and I'm going to refer to them generically as products and customers, but for rideshare companies, they would be drivers and riders. In rental markets, there would be rental properties and renters. And in other cases, they could be physical units and time periods. And in fact, they could be more than two populations. It could be three populations. It could be products, customers, and time periods. But to simplify, to keep things manageable, I'm going to look at this generic case where I think there's a population of products, there's a population of customers, and we can think of the assignment not just at the product level or at the customer level, so not just as a vector of assignments, but as a matrix where the assignment is a matrix where elements are indexed both by product and customers, and can be assigned at that level. And similarly, outcomes can be measured at the level of the product-customer pair. And so, again, at some level, this is kind of the main idea, and the rest is kind of just working out the kind of the implications of that. But we want to think of an experiment as a distribution where we assign the pairs of product customers to the treatment group or the control group. And of course, one reason why this may not have come up much previously, prior to the rise of experimentation in the tech companies, is that in many physical marketplaces, this is hard to imagine. If you and I both go to the same store, to the same supermarket at the same point in time, we of course see the same treatment for all the same products. If a particular product is discounted, it's discounted for both you and me. We can't have a separate discount for you and me when we go to the same store. But at an online marketplace, we can change the treatment for you and me at the same time. You can be given a shipping discount, or you can be given more or less information about a particular product relative to me, even if we visit the marketplace at the same point in time. So the fact that many of these marketplaces are online facilitates this type of experimental design, because you can directly see that that standard experiments are a special case. A customer experiment where we randomize, in this example with these 5 customers and 8 products, where we randomize the customers, is one where every row of the matrix consists of only C's or only T's, and a product experiment is one where every column consists only of C's or T's. And so if the columns only consist of C's or T's, every row is the same. And if the rows are all either C or T, it means that every column is the same. But of course, once you set it up this way, it's very clear that you could do something much more general, that you could allow for variation in the treatment within products, but also within customers in a much more complex way. And we can in fact make the assignment completely random, and that's going to be something that's optimal in some cases. To be specific, that's going to be a very attractive design if there's no interference. But if there's interference between units, then we're going to look for systematic correlation patterns in the assignment to be able to both detect and adjust for some of these interference patterns, these types of interference. And so in particular, and this is going to be the leading design that I'm going to focus on during most of this presentation, we look at what we call a simple multiple randomization design, and that's one that's also mentioned in the Johari et al. Paper, as one where we pick a randomly selected set of products, here products 5 through 8, and a randomly selected set of customers, here customers 3 through 5, and only the product customer pairs where both the products were selected and the customers were selected, so products 5 through 8 for customers 3 to 5 are assigned to the treatment, and every other pair, product customer pair, is assigned to the control group. And what does that do? Fundamentally, the key insight is that it gives us 3 sets of the customer product pairs that are ex ante comparable because of the randomization, but they're only ex ante comparable. Ex post, their average outcomes may be different because of interference between units, between customers, and between products. So here we get these 3 sets of control pairs: the green ones, customers 3 through 5 for products 1 through 4, the red ones, customers 1 and 2 for products 1 through 4, and the blue ones, products 5 through 8 for customers 1 and 2, that are ex ante comparable, but at ex post have different customers. If we look at the green Cs, the customers 3 through 5 for products 1 through 4, they may be affected by the fact that for other products, these customers were exposed to the treatment. So if the treatment makes these customers switch from what may be relatively similar products 1 through 4 to the treated products 5 through 8, suppose the treatment is something that makes the products more attractive. There's a shipping discount or there's more information. Customers may switch to the treated units, and you would see to the treated products, and you would see a systematic difference between outcomes for the red customer product pairs and the green customer product pairs because of this of these spillovers. And similarly, for the red and blue control groups, we might see systematic differences coming from spillovers within products for different customers. And the fact that we see these systematic differences in outcomes is evidence that are spillovers, and we can use those to disentangle direct and indirect effects of the treatment. And that's going to be the theme of this this presentation of this paper. So kind of in general, we think of there being 2 or more populations with outcomes indexed by both. There could be customers or products, drivers or riders, products or days, or drivers, riders, days. We can randomize units from one of the 2 populations and do conventional experiments. But if we can assign the treatment to a pair, if we can vary the treatment both within customers and within products, there's 3 potential benefits to such experimental designs. One is that we can answer standard questions more efficiently if there is no interference, and so these designs can be more powerful for estimating standard objects. But also, if in fact there are spillovers, we can detect that using these designs, and we can adjust for some of those patterns of interference and spillovers. And so now, kind of from now on, I'm going to make this kind of more specific. We're going to look at a case where we have 2 populations, customers and products. We have a treatment that consists of providing more information about products to customers. As I mentioned this before, either pictures instead of just written descriptions, or include reviews. And the question is, what would happen if we exposed all the pairs to the treatment versus we expose none of the pairs to the treatment? And we're interested in measuring the effect of the treatment on some outcome that we can measure at the level of the customer product pair. And again, the key is that in the experiment, we have the ability to vary the treatment at the level of that pair. And there's many cases where that's not possible, even if we have multiple populations and there these designs are not relevant. So kind of back to the simple multiple randomization design here. The questions we're interested in: what are interesting estimates? How do we do the design? What is actually a good distribution over all possible matrices of assignments? So in the standard case, we just have a factor of assignments, and the design consists of a distribution over the binary indicators. Now we have a distribution over this whole matrix of these binary indicators. And so we're interested in what correlation structures we should use there to get good estimates of the things we're interested in. So even in this simple design, we could have more pairs assigned to the treatment, say by, instead of having half the product, we could have 3/4 of the products assigned to the treatment group and more or fewer customers. And whether that's a good thing to do depends on the magnitude of these spillovers. And it depends on exactly what we're interested in. If we're interested in the overall effect of being assigned to the treatment, versus nobody being assigned to the treatment, it's important to have this group be big, but also this group be big. And of course, we can't do both at the same time. And it's going to depend on what we think the structure on the spillovers is, what a good way of doing the design is here. Then, given the particular design, we're interested in estimation. How do we actually estimate these objects? Which treatment group are we going to compare with which control group? And in this case, of course, there's just these 3 control groups. So we can compare the set of treated pairs to one of these 3 treated control groups, but we can do more complicated things. We may compare the treated outcomes to some linear combination of these control groups, and then may adjust for at least some spillovers. And then the last question is how we do inference here. And that's conceptually a relatively straightforward question, though in practice this can be fairly messy. But we just going to create in the designs we're looking at so far a finite number of different groups. For each of these groups, we can estimate the average outcome because of the randomization that's going to be representative of what we would see if any unit was in that treatment group. And so all these averages are going to be double averages over both customers and products, but we can figure out what the randomization-based variance is for all of these averages. And so that allows us to directly do the inference for the average outcomes in any of these groups. And then what we want to do is look at linear combinations of these averages. We can do inference for those linear combinations with the provision that, just like in the Neyman analysis of simple randomized experiments, we can't get an unbiased estimator for the exact variance. We can only get bounds. We can get the conservative estimators for the variance that estimate the bounds on the variance, and that's going to carry over here in a more complex way. There's going to be multiple terms that we can't estimate, but we can put bounds on all of them, so we can do inference in the end. That's going to be conservative in the same spirit. Standard variance estimators for regular experiments are conservative. Now, back for a moment, kind of to the bipartite graph representations in the Ziegler, Meali, and Papa Giorgio work. We can put the design in the same bipartite graph representation, where we have a number of viewer treatments, a number of product treatments, and a set of outcomes that are measured on a different population, with some of the treatments affecting some of the outcomes, but not others, in a way that's governed by the type of interference we're interested in looking for. Okay, now let me look at some specific results. So we're going to look at a setting where we have capital I customers indexed by little I and capital J products. We measure some outcome on the pair customer I and product J, and we assign a treatment to the same pair customer I, product J. The boldface Y and J are the capital I times capital J matrices of outcomes and treatment. And we're going to be interested in what are possible choices for the distribution, the possible designs, where in the standard case, with just a single population, that the answer to the design question is often simple. We should randomly select half the population and to be in the treatment group and half to be in the control group. But here, we want to allow for some correlation within the rows and the columns of the treatment matrix. And exactly what the optimal design there is going to depend on 3 things. The question of what the question of interest is, whether we're directly interested in getting estimates of the spillovers or just the overall average effect of the treatment. It depends on what we think the nature of the spillovers is and what the correlation of outcomes is within rows and columns of the outcome matrix. And so I want to stress here that there's not going to be general kind of generic answers to these questions. We're going to need to make assumptions about what we think the nature of the spillovers is. And I'll give a specific example of the type of assumption we may be willing to make here that could at least give us a starting point for answering these questions. But in some cases, we may be more confident about what the nature of these spillovers is, whether most of it is within customers or within products, and that would affect the optimal design. Now, the easiest case to look at is one where we have a completely, where there's no spillovers at all, where we're confident that treating one particular pair doesn't affect the outcome for any other pair, even if it's the same customer but a different product, or the same product but a different customer. In that case, a very sensible design is one where we randomize kind of both within the products and within the customers. And so we ensure that every product is balanced in terms of its treatment, and every customer is balanced within with regards to its treatment. That's going to be more efficient. It's going to lead to a more powerful experiment than one where we just randomize the products or just randomize the customers, because the same customer is now can be used as a control for different products, and the same product can be used as a control for different customers. And so we want to balance things and kind of to see what the gains are from doing it. Suppose that the potential outcomes satisfy this the fixed effect structure, where there's a customer-specific component alpha I and a product-specific component beta J and some idiosyncratic component. If we do a customer experiment where we randomize the customers, and the same one customer is always in the treatment group or always in the control group, there's a component to the variance of the difference in means estimator. There's a component to that variance that depends on the variance of the customer fixed effect. If we do a product experiment, there's a component, the leading component of the variance depends on the variance of this product fixed effect. But if we do a completely randomized experiment, both the alphas and the betas cancel out in the comparison, because we balance things within customers as well as within products. And the leading term now is of the order 1 over capital I times capital J, and it depends just on the variance of this idiosyncratic term. So we get a much more efficient estimator for the overall average effect in this setting, where there's no interference between the products, and there's no interference, no spillovers within products. Another version of that is actually has a long history in agricultural experimentation, where experiments, say, for different types of feed for livestock, would often use the same the animal as its own control by switching the treatments over time, but switching the different animals to the treatment at different times. And so that's basically the same type of example, where now the two populations are time periods and animals. Because in that type of experiment, the concern often would be that there would be some spillovers over time. If we feed an animal a particular type of feed, we can't switch them the next hour to a different feed, because there might be some time before that feed is out of their system. And so we may only switch them every day or every week, and use some time to let the animal get used to the different feed. So we wouldn't make the time periods very small, because there would still be concern about spillovers. But if these time periods are big enough, those spillovers would be viewed as ignorable. Now let me get to the more interesting designs. So here, what we refer to as this class of simple double randomization designs is one where we first randomize the customers into the 2 or more groups. We randomize the products into 2 or more groups, and then we assign the units to the treatment as a function of these 2 randomized assignments. And so the simple example that I've used before, and I'm going to focus on most of the time, is this case where there's 2 groups for the customers and 2 groups for the products, and only the selected customers and the selected products are in the treatment group. But it could be more groups, and that would allow us to have some customers most of the time exposed to the treatment, and some customers only rarely exposed to the treatment, and some products almost all the time exposed to the treatment, and some products never or rarely exposed to the treatment. And you would get much more variation in the fraction treated customers for each product, and more variation in the fraction treated products for each customer. And that would give you more information to learn about the extent of the spillovers. That doesn't introduce any fundamental complications. It just makes the notation much more complex. So here, the key thing is that we have these 4 ex-ante comparable groups, 3 of which are still exposed to the control treatment. And so we're going to use these 3 groups to learn about the interference. And so to kind of do that, it's useful to give these 4 groups different labels. The pairs that are actually exposed to the treatment, we refer to as the treated group. The red C's we refer to as consistent controls. These are pairs of customers and products where the customers are always in the control group, also for other products, and the products are always in the control group, also for other products. Those are the consistent controls. But then we also have 2 other control groups. The inconsistent customer controls consist of customers, of these customers that are sometimes in the control group, but for other products are in the treatment group. And then we have the blue C's that are product customer pairs, where the customers are always in the control group, but the products are in the treatment group for other customers. And that's going to allow us to learn about the presence of that group is going to allow us to learn about spillovers within products. Now, kind of to think about what things we might be interested in here, I want to look at 3 possible estimates. So to characterize these estimates, it's useful to think about 3 assignment matrices. W indexed by T is the matrix with all elements equal to T. W indexed by C is the matrix with all elements equal to C. And then the third one is the critical one. Here we look at the matrix with all elements equal to C, other than the ij element that is equal to T. So this is an assignment where only pair ij is treated. And so given that we can look at the overall average effect, which is the average outcome if everybody is treated versus the average outcome if nobody is treated. Then we can also look at the average direct effect, which is the average outcome if only pair ij is treated, minus the average outcome if nobody is treated. So that gives you the direct effect of pair ij being treated on the outcome for that pair. Well, and so there's no indirect effect because none of the other pairs are being treated. And then we can look at the average indirect effect, where we look at the outcomes if everybody is treated relative to just per IJ being treated. So now we look at the effect of also treating everybody else to see how that additionally impacts the outcome for per IJ. Now, these are kind of natural things to focus on, but in general, it's going to be very hard to estimate these objects, even if we randomize kind of both the customers and the products in this double randomization design, without additional assumptions that somehow limit how much interference, how much spillovers there are between units. And so one of the key assumptions we are considering here, and I don't want to sell that as an assumption that is particularly plausible in cases, but it's a natural one that kind of limits the spillovers to what in many cases would be the first order spillovers. So here we assume that the potential outcome for a particular customer product pair depends on three things. One, the own treatment, and then the spillovers come only through two objects, the fraction treated products for that particular customer and the fraction treated customers for that particular product. Again, this is a very strong assumption. So it means that treating customer 2 and product 2 can not affect what happens to customer 1 and product 1. The spillovers are only within rows of the table and within columns within rows of the matrix and within columns of the matrix, but they don't cascade further down. And in many cases, for example, in the settings Monroe, Waage, consider spillovers may cascade down through the effects on prices in a way that allows treating one customer product pair to affect outcomes for a completely different customer product pair. Here we kind of limiting things that allows us to get some exact results for these cases, and kind of more substantively, we make the case in the paper that the first order spillovers would typically come through the fraction treated products for a customer and the fraction treated customers for a product. Now, given that assumption, that local interference assumption, we can now think of the potential outcomes as being indexed by three objects: the scalar binary treatment for that particular unit, and the fraction treated customers and the fraction treated products. And so we can define the averages of those potential outcomes over all units, over all pairs in the population. And then if you have the type of double randomized experiment that we looked at before, where we have a fixed fraction of treated customers and a fixed fraction of treated products, the average outcomes in these four groups can now be expressed in terms of these population averages of the potential outcomes. And it kind of shows you a little bit what the difficulties are going to be. What we might be interested in is objects like Y1, 1, 1. The average outcome if the unit is treated itself and everybody else is, all the other customers and all the other products are treated relative to what we would see if nobody was treated. But we can't get at those directly because we can't vary the fraction of treated customers from 0 to 1 and the fraction of treated products from 0 to 1, both at the same time in the same experiment. We can only, within this class of experiments, the only objects we can get are these four for particular values of P and Q. And so if we make P and Q very small, we can get close to estimating this type of object, but we wouldn't get very precise estimate of of this thing, because there would be very few treated pairs. So it's going to be tricky to estimate differences of this type in general. Now, what can we do? We sort of have these 4 groups, and so there's a number of direct comparisons we can do, and I just mention 5 of them that are particularly natural. One is we could compare the 3 outcomes for the treated units, the treated pairs, and all the control pairs. That's kind of a little difficult to interpret, and it's easy to look at the other 4. We could compare the average outcome for the treated pairs with the average outcome for the consistent controls. And what that's estimating is the average of the local interference. It's estimating the average outcome evaluated at 1 P and Q minus the average outcome at 0, 0, 0. And if P and Q are relatively large, that's informative about the total effect of the intervention. We can also compare the average outcome for the inconsistent product pairs to the consistent controls. And that's telling us something directly about spillovers within products. Exactly what it's telling us about that depends on the value of P, of how many the customers are assigned to the treatment, but it is telling us something directly about the spillovers within products. Comparing the inconsistent customers versus the consistent controls tells us something about the spillovers within customers. And then the last interesting comparison is one where we do a difference in differences type comparison, and that tells us, at least under additivity of the spillovers within customers and their products, it tells us something about the direct effect of the treatment. Okay, so what this illustrates is that there's going to be challenges in estimating some overall effect of these spillovers, but at least under some conditions, in particular, if we're willing to make additivity assumptions, we can learn something about both the direct effects of the treatments and the indirect effect of the treatments, as well as the total effects. Now, let me also make a couple of comments on how we would do inference for any of these 4 averages in these 4 groups. The natural way of estimating these averages, of course, is just take the double average. Then to get at the variance, we're going to look at within the row and within column the variance of the outcomes, as well as the within column within row the variance, and we get the following expression for the estimated variance of the average outcome in each of these 4 groups. And so this particular expression is going to be unbiased for the variance of the average outcome in that particular set of customer product pairs. Now, that only gives you the variance for these actual averages. What we're going to be most interested in is variances of differences in these averages, or even more complex linear combinations. We also have expressions for those. There we cannot get unbiased estimators for these variants, because we can't get unbiased estimators for the covariance of 2 of these averages, but we can bound those covariances, and that gives us conservative estimators for the variance that we can use to construct confidence intervals that are going to be conservative, just as in the standard case. Okay, let me then finish up with 2 comments kind of about even more complex experiments that fit within this class. And so one set of experimental designs we've been looking at is what we refer to as equilibrium designs. There we're directly trying to figure out kind of how the new equilibrium arises in settings where, say, the sellers for each of these products may adjust their prices in response to the treatment shifting demand away from treated to control pairs. And so what we do here is do a two-stage randomization, where first we assign the customers to two groups here labeled A and B. And then within the set of customers assigned to the A group, we do a customer experiment. We kind of re-randomize the customers. Some of them are in the control group, some of them are in the treatment group. Sorry, I misspoke there. We first assign the products to two groups, A or B. And for the products in group A, we do a customer experiment where customers are either always in the treatment group or always in the control group, at least for those products, for these first 8 products. In the second group of products 9 through 14, the ones assigned to the B group here, we do a product experiment where now each of the products are assigned to the treatment or control group for all 10 customers. And so just like before, just like in the double randomization design, in the simple double randomization design, we get 3 different sets of control customer product pairs, the green, red, and blue. But now we also get 3 different sets of the customer product treatment group pairs that allow us to learn about the different types of interference. And so this is going to get us 6 groups overall that allows us to kind of learn about complex the spillover patterns. The second type of additional designs beyond the simple randomization, double randomization designs is to do the multiple randomization for clustering problems. And so here what we do is we assign the customers to and we divide the customers into 2 groups, A and B. And for the customers in group A, we do a cluster randomized experiment where we assign so the products are divided, partitioned in clusters. We assign all the products in a particular cluster to the treatment or control group for that set of customers. And for the customers assigned to group B, we do a regular product experiment where we pay no attention to the clusters. And now within the same experiment, within this single experiment, we can not just get estimates of the overall effect of the treatment, but we can also get estimates of the spillovers within clusters. So we actually see we learn what we should do for the future, whether we should actually be worried about these within cluster spillovers. So let me then conclude here. So what we're doing here, what we're excited about is the fact that in these settings, kind of with multiple populations, there's a host of new experimental designs possible. Once we kind of realize that you can think of the assignment of the experimental design as not just choosing a factor of treatments for population of units, but think of it as choosing a distribution for a matrix of treatments for pairs of customers and products, or pairs of drivers and riders. There's just a host of new possibilities for getting designs that are effective at answering the specific questions we're interested in. And these designs can both answer the standard questions about what the overall effect of the treatment is more efficiently, more effectively than standard experimental designs. But they also allow us to answer questions that standard experimental designs can't answer. But this is creating a lot of new possibilities, but also a lot of challenges. So we now experimental design questions become much more complex, and there's going to be many settings where the answers are going to be quite different. We can learn about spillovers, but that's going to create more challenges for doing inferences. And the key thing, and in some sense, that's kind of the most exciting part of this, it requires us to kind of think very hard about exactly the nature of these spillovers. And in some of these marketplaces, the particular design of these marketplaces creates the structure, tells us exactly what the structure is of these spillovers. In a rideshare company, my actions as a driver affect other riders, but only in a very limited, in a very anonymous way. What I do only affects other riders to the extent that my decision to get a ride on a particular day limits the number of drivers available at that particular point. So we have a lot of information about this structure that should help us guide the design questions and guide the inference questions for these problems. So I think there's kind of lots more questions here that we haven't really dealt with in the paper. There's a paper on archive looking at these methods, but I think there's still a lot more to be done, a lot of exciting questions. So let me stop here. And again, let me apologize for not being there in person. I wish I had been able to do that. I'm not sure whether there's any time for questions at this point, Annie. But let me stop sharing my screen here.
Okay, let's thank Guido first. We'll have time for a couple of questions or comments. Yes, there is one there and one here. Can I bring the...
Sorry, I can hear a lot of noise, but I didn't hear a question.
Hello.
Okay.
Yes.
You'll be able to hear that.
Yeah.
Hi, this is Michael Stein, Rutgers University. If the treatment is a discount, what would happen if customers started communicating with each other on a nearly real-time basis so that they would know, oh, someone else is getting a deal I'm not getting? That would seem to make things much more difficult.
Yes, that would create a lot of problems. So here, this is more effective. And so I think that is one reason why the type of experiment, when some of these companies do these experiments, they limit a lot the heterogeneity in treatments they assign to different customers. And so they may randomize over time or over geographic markets rather than over individuals. But for some treatments, having different people exposed to different experiences may, first of all, not directly be detectable. If search algorithms are changed a bit, that wouldn't directly be detectable, and so there it would not be a problem. But this is in principle designed for settings where the spillovers are directly mediated by things we can see, and there's no outside communication.
Thank you. We have another question, please.
Okay, thank you. Andres Rakar, University of Ljubljana. It was a very interesting lecture. Hi, Guido. Basically, two questions, short questions, but why this opens up a lot of questions. I think, firstly, there is also in the audience, Stefan Wager. There is a paper of Wager and Lee related to graphone asymptotics. And as you have shown this connection to networks, could this problem, this would be a logical extension, be studied in a network in a Greffon asymptotic setting? And secondly, I think that in your archive paper, you study triple randomization also design. How could this be extended, probably to tensorial or similar settings, to higher, one could say, order maybe randomizations? Thanks.
Yeah, I mean, I think good to see you there. And again, I'm sorry I'm not there in person. And so I have been talking to Stefan about some of these problems many times. He's down the hallway for me most of the time when he's not in Florence. But I think it's sort of partly there's a lot of different ways of approaching these problems. So here we were initially focused on trying to get exact kind of randomization based results of the type of the Fisher-Neyman type in this setting, but it's clear that we need to also use an asymptotic approximation, and the type of work Stefan's done is going to be very helpful for that. As I said, there's kind of a lot of additional work to be done here.
Okay. Thanks a lot, Guido. We have the last, probably last question by Georgia.
Hi, it's Georgia. So a really nice talk and nice paper. I wanted to ask you, in these companies, hi, in these companies, a lot of times they do these experiments in batches. Have you thought about, if we learn how the spillovers happen within products or within customers, whether that will help us in some way design a next experimentation strategy that targets the spillover that is larger of the two in some sense? So are you thinking of extending this type of work to these kind of like, adaptive experimental designs where you learn the spillover, how the spillovers occur, and then you target those specifically?
Yeah, I mean, again, that's a really interesting direction to go in, and I was sort of hinting at that a little bit with these clustering type experiments. In many sort of what I've seen sort of in many of these companies, they're very cognizant of the fact that there are spillovers, and often the way these spillovers are being handled is by aggregating units into sets such that the spillovers are relatively limited. But how much aggregation you do is not quite clear, and it's very costly to do that aggregation because it makes the experimentation much less powerful, much less efficient. And so it's very important to have ways of limiting the amount of aggregation you do when it's not necessary. And so using some kind of adaptivity to figure out within an experiment how important it is to do the aggregation is going to be very helpful. And the last type of experiment I described, kind of where within the same experiment you actually learn about the clustering type spillovers, so that within that for the future you can do a more efficient experiment. It was one way of going in that direction, but you could do it even more effectively within the same experiment by changing the level of aggregation in the experiment over time.
All right, thanks a lot. I think we can thank Guido again, and
Thanks. And again, my apologies for not being there in person.
thank you.